All right, so yesterday we left off talking about how to add and subtract significant figures and multiply and divide them. So with multiplying and dividing, our answer can only be as accurate as what? The least accurate number or the least precise number. And how do we know which one is the least precise? The one with the... Not for multiplying and dividing. The least number of significant figures. Okay? So when we multiply and divide numbers or measurements, we go by our answer can only have as many significant figures as the least number of significant figures in the problem. Okay, so what about adding and subtracting? Our answer can only have what?
Least amount of digits.
Least amount of decimal places. That's correct. So our answer has to have the smallest number of decimal places, the same number as the smallest number of decimal places. So if we were to add up, well, if we use their numbers again, we were to add up 16.74, 5.1, and 21.8. How many decimal places should my answer have? 1. Because 1 is the least number of decimal places in 2 of my measurements. So my answer should only have 1 decimal place. Good. All right, so scientific notation should be a lot of review for y'all. So I'm going to go through it pretty quick. But, with scientific notation, that you just take, it's usually you have a number between 1 and 10. And then out beside that, you have the power of 10. And the power of 10 tells you how many places you moved the decimal to get behind that first non-zero digit. So if we use the example of 2,500, okay, and the decimal is behind or at the end of that number, then we're going to move that decimal 1, 2, 3 places. It needs to be behind the first the first digit. It needs to be behind the first digit in the number. Okay, so that's what we mean by it has to be between 1 and 10. It can't be behind the 5. It can't be 25. It has to be between the 2 and the 5. So it has to be a digit between 1 and 10, and then your decimal place. So we had to move it 3 places to the left. So that means it's going to be 2.5 times 10 to the 3, because we went 3 places to the left. If it's to the 3, then that means it's positive. Oh, I got a sick grandbaby. She has her first cold and fever. So she just sent me pictures. Her eyes were all swollen and red, and I know, it's pitiful. She didn't take her to the doctor. But she's on the mend, I think. All right, so here is our answer, 2.5 times 10 to the 3. Now, the other good thing about writing numbers in scientific notation is the number part, all of those digits in there are significant. We have to write them as significant. So when we say 2.5 times 10 to the 3, how many significant digits are in that number? 2. The 2 and the 5. All right, so what if I wrote this? What if I wrote, let me erase that. What if I wrote 2.50 times 10 to the 3? How many numbers are significant? 3. Because the 0 is behind the number and behind the decimal, then it makes it significant. So those are 3 significant figures. I'm sure in my measurement that the 2 is right, the 5 is right, and the 0 is the one I'm uncertain about. So all of those are significant. Yes, ma'am.
So what if it's like 0.005, like
Okay,
how
so-
many zeros are?
Okay. That one isn't going to be scientific notation, but if you're just talking about looking at the number, 0.005, is that what you're saying?
Yes, ma'am, or just
Okay.
any zeros after the decimal, but before the numbers.
Okay. Any zeros after decimal, but before the number. I just had brain. Hang on.
Those are significant.
Let me think on that. Yeah, those are significant. Yes. It's the ones after that that may not be.
Okay. Would the 2.50 not be like an incorrect scientific notation though? Like
No, it'd be fine.
Oh, you can leave an O there
Mhm.
or zero, sorry.
Yes. Now, see, this is where kids get confused with math. Because what have you always been taught in math? You can drop it off. Doesn't matter, right? But if it's a measurement, it matters because I know I'm measuring out to the hundredths place. And you have to indicate that you're measuring out to the hundredths place with certainty. Okay, so you can't just drop it off. So what if we had 2.500 times 10 to the third? How many significant figures would that be? 4. And the reason that it's 4 is because I'm saying in that measurement, I am sure that I measured out to the thousandths place with precision. So I'm sure about that last decimal place, and that's why I have to write it down. Okay. All right. So let's clear that screen. Go back. All right, order of magnitude. Remember, order of magnitude is just a power of 10. And so sometimes we can use order of magnitude to get an estimation of something or get in the ballpark where you may be off by some, but it's okay. Okay. So there's an example. We're not going to have to do that a whole lot, but there's an example of what we're talking about with that. Suppose you want to estimate the speed of a cliff diver on entering the water. First, the cliff may be 10 meters high. It's not going to be 1 meter because 1 meter is not a cliff, right? That's just a step. It's probably not going to be higher than 10 to the 2 meters because that's 100 meters. That's really tall. Okay? So most of the time, somebody's not going to dive off a cliff that's on 100 meters high. So we don't need to worry about that number. And that 1 is too small, so that's why we estimate probably around 10. Okay? Then the diver hits the water in something like 1 second. So again, we're going to estimate 1 second. It's probably not going to be 0.1 seconds because that's too short of a time. And it's probably not going to be 10 seconds because that would be a long time in the air. Okay? So we estimate 1 second. So we're estimating his speed when he hits the water is going to be the 10 meters for how tall the cliff is, and the 1 second for the time he spent in the air. And that's just an estimate. We could be off. But we're using powers of 10 to make that math really easy. Okay? All right. Okay, we'll move on from that. Graphing. The reason we graph things is to see trends easily. So we have a data table, and when we can see a trend, but if we put it in a graph, we can see that trend really easily, and we can also get a lot more information about it. Slope is really, really important. So knowing how to find the slope of something is going to be very important because in here, the slope is not just the word slope. It's actually going to mean something. It's going to show a relationship between two things. Okay, so if you look at this graph, we are graphing velocity and time, okay, or speed and time. So the slope of that line is going to mean something. It's going to be a constant number. Okay? All right. Whoops, wait a minute. So by looking at this, you can predict how fast is the ball going to go in 7 seconds. How did you get that?
See the trend. Each time it's like passes 1 second, it's 10 meters per second.
Exactly. You can see the trend, and you can see that even though 7 is not on this graph, we can still predict what it should be by looking at what happens every other time. Okay? So it's going up 10 meters per second each time, so by the time we get to 7, it should be 70 meters per second. That's called extrapolation. So we're looking at something beyond what's actually on the graph. It's extra, beyond the graph. But we're assuming the trend's going to be the same, so we just follow that. What about at 2.5 seconds? 25. How'd you get that? It's on the graph. Well, how did you find it? On the graph. Be very specific. Huh? I went over to 2.5, and then what did I do? Go up. And then what? Go up. And that should hit right at about 25. Okay? That's called interpolation, because I'm doing something within the graph. I'm looking at a number that's within the graph. Okay? All right. So in general, linear relationships are going to exist between two quantities that form a straight line. So y'all know that. You might, if you got to write that down, that's fine. But just remember, linear means it's a straight line, and it shows a relationship between those two things. And that relationship is a straight line. Okay? Unfortunately, not all graphs are straight lines. Sometimes they are curved lines. Okay? So let's look at this example. All right, so suppose we measure the distance covered by a soccer ball, and we plot the data during each second of the ball's motion. We call this a nonlinear graph, obvious reasons. It's also called a parabolic relationship. So if you remember back to algebra, what's a parabola? Where it makes that little U shape. And what we have is half of a parabola right here. Okay, so it's a parabolic relationship. Okay. So if a graph is not constant or is not linear, then the upward shape is a parabola, and this is the general formula. You're going to have an exponent in there. So if you go back and think about your algebra, slope-intercept, y equals mx plus b, that's only for what? Straight lines. Those are linear graphs. But you have general equations for parabolas and hyperbolas and all of those other things too. If you got a parabola, you are going to have an exponent in there, right? So we say that it's the position on that graph is equal to some constant times t squared. The square is what makes it go up in that parabola shape rather than being a straight line, okay? So anytime you see that, you ought to associate that, oh, okay, this is a parabola, we got a square, we got an exponent in here somewhere. It's not just y equals mx plus b, okay? So I would draw me a little sketch of the parabola graph, and then I would put this little formula out beside it, and if I'm taking notes, and so that you make sure you understand that relationship. Parabola means you're going to have a square in there. You're going to have an exponent in there. This is just math related. Does anybody know what this constant is going to do to my parabola?
Change the y value.
It's going to change the y value. So what does that do to the shape of the parabola? It's going to make it wider, or it's going to make it narrower. What if we had a negative in front of that? What would that do to flip? It would flip it upside down. Right. Okay. Good. Oops. Okay, so this would be, finally, we can do measurements of volume of a container with pressure. So that should look kind of familiar from chemistry because remember, pressure and volume are indirectly related. Okay, so as volume increases, pressure goes down. And that's what you see on the graph. Okay, so as we go up in volume, our pressure goes down. So that's an inverse relationship. Okay. And then so here is our equation. The pressure is equal to some constant divided by the volume. So if it's an inverse relationship, you're going to get that hyperbola. Remember those are from, that's not geometry, that's algebra 2. But that's a hyperbola. So as one thing goes up, the other thing goes down, and you make that hyperbola type shape. Okay.
So,
Yes.
do they write constant just to avoid having a ton of x's?
They write constant because that's going to be a set number all the time. So when we did ideal gas law, remember, was PV equals nRT, and that was a constant. It was the same number all the time, right? So that's what they're talking about, that there's going to be some number that's the same all the time that you're going to put in there. A lot of the constants that you'll use in here, speed of light is a constant. It doesn't change. Acceleration due to gravity does not change. That'll be another constant that you memorize and that you'll be putting in. So that when they're writing a constant, that's what they're talking about, a value that doesn't change. Okay. All right, so this is going to be new. You probably not used or heard these words before. So scalar quantities are quantities that are represented by a number with a unit. So if I measure something and I say it is 48 meters, that is what we call a scalar quantity. It's a number and a unit, and that's it. Okay? So if I'm measuring the distance of this room from here to this wall, that is a scalar quantity. I would just take my ruler and I would measure that distance. Okay? And here's some other examples of scalar quantities. Temperature, speed. If I'm driving down the road and my speedometer says I'm going 25 meters per second, that's a scalar, or I think that's what we did yesterday, 65 miles per hour, what we're used to saying. That's a scalar quantity. It's a number and a unit, and that's all it tells me, okay? So other quantities, though, are known as vectors. So vectors are things that have a numerical value with its unit and a direction. Okay, so it's a way to get things a little more specific. So I can say I'm going 65 miles an hour down the highway. What does that tell you? It tells me how fast I go. Does it tell me where I'm going? Does it tell me anything else at all? I'm on the highway. But there's lots of highways, right? Highways go in all 4 directions. So if I want, that's a scalar quantity. But if I'm saying I'm going north on I-65 at 65 miles per hour, what does that tell me? You know which direction on 65 I'm going. I'm traveling north. Okay? So that is a vector quantity because it tells me the direction in which I'm going. Okay? Now, When I say north, that's kind of a vague direction, just north. When we do problems with these, not only are we going to have north or south or east or west, we're going to have a degrees associated with it. You know, you might be going 50 degrees north, 40 degrees, whatever, okay? So we're going to get kind of specific with that later on. So here's our example. Speed of a car is 25 meters per second, but if we combine that with a direction, we have to write out both. So for it to be a vector quantity, you have to write the number, the unit, and the direction. Okay, so 25 meters per second, north. You can put a capital N or S or whatever, but you have to put direction for a vector. Velocity, okay, so you might want to make a note of this because a lot of times people will get this confused. Velocity is a vector quantity. Speed is a scalar quantity. Velocity tells me how fast I'm going and in what direction. Okay? But speed just tells me how fast I'm going. Yes?
So, question. So velocity, okay, so that stems from the word vector, I guess.
Well, yeah.
So,
But there's other vector quantities.
is velocity just like the dimension of like speed or whatever, while vectors could be whatever other dimension, whatever?
Exactly, yes.
Okay.
Yes, we can have other types of dimensions that are, and we're going to have other types of dimensions that are vector quantities. We talk about different forces. We talk about force of friction, and those are the two that pop in my head right now.
But velocity is specifically like.
Velocity is how fast you're going and in what direction. Yes. Okay, so everybody have this down? Because this is kind of new stuff that we need to make sure we have written down. Everybody got it? Okay. The key to remember is that vectors, and we've already talked about this, vectors have a numerical value, and we call that a magnitude. So you might want to jot that down just because that's a term that you might hear. The numerical value on something is called its magnitude and direction. So vectors have magnitude and direction. Scalars just have magnitude. Magnitude means the number and its units. That's it. So if I'm going 65 miles per hour north, what's the magnitude of that?
65
The 65 miles per hour. Okay? The direction is the north part. So vectors have magnitude and direction. Scalar just have magnitude. I think that's going to take us through 1.4. 1.5 is really short because it's just listing out some problem-solving skills, and then we're going to actually start working some problems because the best way to learn problem-solving skills is to work problems, unfortunately. So, does everybody have this down? So the only thing in 1.5 we're going to do is I'm going to give you a list of skills, problem-solving skills or steps to take, and then we'll just spend the rest of the time looking at problems. All right. So this whole class, whether we're doing an experiment in lab or whatever we're doing, you are going to be working lots of word problems. Because like I said, that's real world. Wherever you go to work, if you're in my husband solves problems too. He works in a bank. He says he doesn't use algebra, but he really does. He just doesn't want to admit it. Anytime you put a formula in a spreadsheet, what are you doing? You're using algebra. I mean, And that's why all his stuff is on Excel spreadsheets. He's like, I don't ever use that. Oh, you do. My son-in-law is a electrical engineer at the IP plant down in Pine Hill, so way down south. And his job is to fix stuff. Machine breaks, he's got to fix it. Okay? So when he has a problem, nobody gives him a math formula and says, here, solve this problem. No, his is, that machine's not running the way it's supposed to be running. I got to figure out why, and I got to figure out how to fix it. Okay? So that's problem solving. That works to a point, and then you just got to use your brain. All right. So, all of us are not going to solve problems exactly the same way. We saw with dimensional analysis, there's several different ways you can get to the same end. It doesn't mean that one's right and one's wrong. The same thing here. As long as you are on the right track and you're using the right set of equations and you're making sure your dimensions are consistent, then Carson may work it one way and Adam, you may work it out another, and that doesn't mean y'all need to argue over it because you know what? You both can be right. All right? So here are your steps. Just write down the bold terms. So number one, you got to read the problem carefully. First step, read the problem carefully. It means you might have to read it 2 or 3 times. And reading it is not typing it into the Google search bar. Read it, okay? Read it. Number 2, and this is going to be something we do a lot that you may not have done in math class very much, but we're going to sketch out the problem. Especially when we start talking about vectors and forces and velocity and acceleration, it's going to be extremely helpful for you to sketch that problem out so that you know and you can visually see, here's what I'm given, here's the directions, here's where, here's what my answer needs to be. Okay, so you need to sketch out the problem. It's going to help you understand what you're given and what you're looking for. Visualize the process is kind of the same thing as sketching, but you want to think about the problem and what's going on and kind of visualize it like a movie reel going on in your head. What's happening? All of those things require you to think. You can't just read and stuff. You've got to be actively thinking about that problem. You can't be multitasking a whole lot. Okay, so everybody got those 3? Read, sketch, visualize. Then strategize. On the strategize part, that basically means, all right, here's what I'm given. Here's what I'm asked to find. What formula or law is going to help me do that? Okay? And you're just going to kind of go through your list of different equations and different laws that may help you find that. Identify appropriate equations and then solve the equation. And there's actually 2 more, I think. You think, oh, well, I solved the equation, I'm done, right? Nope, not quite. It's that thing your math teacher always tells you to do, but very few times do we actually do it. What is that? Check your work. Check your work. Does it make sense? Okay, does it make sense? And in here, are my units working out correctly? Because your units are going to be one of the biggest helps for knowing whether or not you got an answer right or wrong. So you want to make sure those units are dimensionally consistent. You want to make sure all your units have canceled out correctly. And then you want to make sure is this a reasonable number? Okay, does that make sense? Explore limits in special cases would be the second one. All right. Okay, so we are done with that. Let's look at a couple of examples. How do I get rid of this part? In slideshow display settings. Okay, anyway. All right, so here's a couple of examples. Oh, you can see that. Oh, duh, I'm so dumb. Okay, there we go. All right, so E. coli bacteria is about 0.005 millimeters in length. Convert this length to meters. So this is just a unit multiplier example. So again, we're going to, our dimensional analysis, we're going to put millimeters on the bottom because that's what we want to get rid of. And we're going to change that. They changed that to scientific notation just because it makes things a little bit easier. For some people, if you don't think it makes it easier, don't put it in scientific notation. It's okay. So we have 5 times 10 to the negative 3, or 0.005, divided by 1,000, and that gives us 5 times 10 to the negative 6. Okay. So any questions on dimensional analysis or unit multipliers? Okay. And I'm not going to spend tons of time on that. If we're good with that. I don't think we need to do that. And that's just more of the same. But remember, you're ultimately going to have to find volume. So you're going to do your unit conversions, which they did over here. And then you're going to multiply all 3 of those. Once you get the units correctly, you'll multiply all 3 of those together to get your volume. Okay, which that shouldn't be too big deal. And we did that yesterday too. Moving on. Okay, so let's take a look at significant figures here. All right, so a tortoise races a rabbit by walking at a constant speed of 2.5 centimeters per second for 52.23 seconds. How much distance does the tortoise cover? Okay, so you need to remember your formula. Or before we even start that, let's practice our strategies. We read the problem, okay? Then we need to try and visualize what's happening. So we got a tortoise and a rabbit. I don't know if you can see, but there's the rabbit. Okay. So we've kind of sketched it out. The tortoise is going 2.51 meters per second. That's one of the things that we're given. We know that. And we know that the tortoise's time is 52.23 seconds. Do we care anything at all about the rabbit? No, we don't. So we're just going to ignore him. Forget that. So what equation should we use? We have speed and we have time. And we're looking for distance. So what equation relates speed and time and distance? Yeah. Or it's written in the book as velocity equals distance over time. Okay? Now, so that's our equation we're going to use, but which one of those are we actually looking for? The V, the T, or the D? The D. We're looking for distance. We're looking for distance. Okay? So now we're gonna plug our numbers in. We got 2.51 centimeters per second equals distance over 52.23 seconds. Now, if you like to rearrange your equations before you put your numbers in, that's fine, you can do that. And then put your numbers in last. Or you can plug in the numbers and just solve for the one that's left. So how are we going to get D by itself? Multiply both sides by 52.23. Don't forget your units. Oops. So our seconds cancel out, that cancels out. Distance is equal to whatever 52.23 times 2.51 is how many centimeters. So multiply that on your calculator and tell me what you get. 52.23 times 2.51. Speed. I know it's a V. And I know that's confusing. But it's speed. That's not velocity. How do you know? How do you know that's not velocity? There's no direction there. This says 2.51 centimeters.
So is V always speed?
Mm-hmm.
How would you do that? Velocity.
We'll get to that one later.
Okay, so why would they do that?
I don't know.
So
Just because they want to mess with your head. I don't know. Somebody a long time ago messed up.
okay, so speed is the time.
It's the distance over time.
Distance over time. Length over time.
Length over time.
Oh, I've seen the
Length,
V everywhere
distance.
with length over time, but I was thinking that was velocity. But we just learned the definition. Okay, so V, length over time, speed.
Okay, so what is 52.23 times 2.51? 131 point what? 0.0973 centimeters. So we are confident of that distance out to the 10,000th decimal place? Ew. How many significant figures should my answer have?
3.
Some say 3, some say 2. Justify your answer.
2 plus an estimate, so 3.
How many significant figures does this number have?
4.
4. 52.23 has 4. How many does this number have? 3. So how many should my answer have? 3. 1, 3, 1. 131 centimeters.
So question.
Yeah.
Assuming that you did have 4, do you round that 97 up to a 1? Like, when does rounding work in physics? Ever?
The same way it does in math.
So, like, that's definitely roundable, right?
If you needed 4 significant figures, you'd look at that 0 and then you'd round it just like you would any other number. I look at the 9 and that would round up to 1. It'd be 31.1.
Okay, so you can round it.
Yes, math. That's math rules. That's the thing. Rounding's rounding. Yeah. Okay. So When you write an answer in physics, it always has to be in the correct number of significant figures. Okay, so don't just give me 31.0973 and don't say, well, I'm going to round it to 2 decimal places because we always say round to 2 decimal places. No, it needs to be correct number of significant figures. Okay, so go back through your rules, and it's just practice. It's just practice. Okay. For multiplying, you pick the least number of significant figures, and that's how many's got to be in your answer. Okay? All right, let's try another example. You and Brittany pick some blackberries. Your flat has a mass of 5.7 kilograms. Brittany's has a mass of 3.25 kilograms. What is the combined mass of the blueberries? So, now, I'm going to have to trust you. Don't read the solution part. Try to figure it out. Okay? So, I mean, I can't make it any smaller or bigger, and I can't get rid of that. I wish I could. Wish I could hide it. But, all right, so here's what we got. We got 5.7 kilograms, and we have 3.25 kilograms, and we are looking for the combined mass. What does combined mass mean we're going to do? Add them together, all right? So add them together and give me the correct answer in correct significant figures. Do that on your paper right now. Don't read the solution. And stand in front of it. So find the combined mass of these two things right here in correct significant figures.
It's 9.0. What? Well, 5.7 plus 3.5, that's 8.95. But
All right, okay. All right, so let's add these. So our first job is we gotta add them together. So that's 5, that's 9, that's 8. 8.95 kilograms, all right? That's not correct significant figures. So how do I figure out what they're gonna be?
It's addition, so you
Addition.
just need the lowest number of decimal places.
Exactly, I need the lowest number of decimal places, which means I'm gonna have how many decimal places? 1. So I need this number and I need 1 decimal place. Well, that's a 9 and the number behind it is a 5. So what's going to happen? 5 is going to round up to 9. And so that's going to mean it's 9.0 kilograms. Can I drop off that 0 and just say 9? No, I cannot. I have to leave it and have 1 decimal place. Okay? Good? Bad? All right. Okay, so just looking at these numbers, I don't know if you can see them or not. Again, don't worry about the solution. All right, how many significant figures are in that number? 4. 2.00. I have the 2 zeros tell me how accurately I'm measuring that number out to. What about B? 2. What about C? 2. Because I just look at that. That's the beauty of putting things in scientific notation. So just look at the little number in front of the times 10. What do I do? What about this one? 3.
Okay, so question.
Uh-huh.
Assuming that, like, I don't know, I forget how to do something, and I have a tiny number, can I just put it in scientific notation and be like, okay, now I know something? Or does that not work?
No, that won't work for you putting it in sig figs. You would have to know your significant figures beforehand.
I mean,
But
I feel
if they give you the measurement in sig figs, if they give you the measurement in sig figs, it makes it easy because all you do is look at that number. But you would have to know that this is.
What if it's positive?
yeah,
You would have to if you're given that, you would have to know how many significant figures are based on that.
how many is that?
1, 2, 3.
So the zeros before are insignificant.
They're just placeholders.
Oh.
Doesn't matter.
Then what about
Even
the
if
zero
there's a
plus
decimal before.
0.5 that we
Because there's a 0 before, in order for zeros to be significant, they have to come after a decimal and after a number. Both. Okay. They have to come after a number and after a decimal.
And so what if the exponent was positive? Would all those zeros work?
All right, if the exponent was positive, times 10 to the 3, okay, that would mean 2, 1, 0, 0.
Now you have 4.
So you would have to put your line right there. Remember that line we were talking about? The line, if you can't put a decimal in there, the line indicates where the significant figure is. So you'd have to put a line over that first 0.
So it's 3.
So it's 3. It's still 3 because right here, that's 3 digits, right?
Alright.
So you're gotta have 3.
Sound good.
All right. So what time are we at? We have what, 7 minutes left? No, we have 5 minutes. 7. All right. See. What is homework? Take a picture of it, upload it to school. Yeah. So last night's homework, I gave you homework last night, all right? Make sure you take a picture of it, upload it to Schoology. I'm gonna give you back what you've given me so far, so that you can put it back in your notebook and have it. And I don't have a collection of papers up here.
I need to turn this piano on. Okay, I thought I had my shear formations in here. Shoot, you're gonna make me a little. Good job.
Bro, it's just out of the lunch, we need to take a sip of it.
Dude, I was just talking about it last night.
You know, that's my kind of person right there.
It is.
I'm really wearing it.
All right. Okay, so we have about 5 minutes left. You may work on tonight's homework, which is 30 through 38. You can't stand up, no, can't stand up, do that for 5 minutes.
Bring it 50 or 55.
Oh, no. It rings at 50, never mind. Well, we still got to stay in our seats. Sorry. You may, yes, y'all don't have to ask, just make sure they come back. Some point, come back.
This book is super greasy.
Greasy as in actually greasy, or is that some newfangled term, y'all?
No, it's like,
Yeah, it's not
it-
for
for some reason, it has a picture of a pizza and it smells like.
I got the frame.
Are you teaching a math class?
Yeah, I got one last year.
What is it?
What math?
Mathematics, modeling mathematics, algebra.
I was gonna take that, but they said that, that is not necessary.
You need to take something much harder.
Well, you see, I was gonna just skip
Much
that.
harder. No, you need to be bored stiff on the people around.
I would take math.
So, no, I would pick you out. You need much more of a challenge.
I saw it the other day and I was like, oh.
All right, y'all have a good day.
For some reason, I guess when I was in the shower today or something, I saw the water.
Have all the
on my
forms.
Oh, thank you.
And I
Thanks
was
very
like,
much.
is this the board of
Don't forget, lab donation, $15 would be greatly appreciated.
Bye, Miss Tater.
Bye.
Hello, Cory.